Hello student, our compulsory theory course Physics of Semiconductor Devices, and now we will start our second module PN junction, and from that today we will say topic types of semiconductor and basic device technology of a PN junction. Then this module 2 will mainly uh, going through the different topics as the types of semiconductor, means the direct and indirect bandgap semiconductor, how they are distinguished each other with the different points. Then fabrication of PN junction, that is a basic device technology. Then depletion region, depletion layer capacitance, then IV characteristics for Shockley equation, then generation recombination process. As like previous chapter we'll see, now we have to go for PN junction, then a high injection condition, diffusion capacitance, and various types of junction breakdown also we'll see in the chapter. Then topics to be covered in the today lecture is that today we'll go for the what is meant by direct bandgap semiconductor and indirect bandgap semiconductor, and then how we distinguish these two types of semiconductor, then which will follow by the thermal equilibrium condition for the PN junction, then equilibrium Fermi levels, and from that we'll go also for the space charge region and fabrication of PN junction, which is followed by there is some numericals of that. Then see a direct bandgap semiconductor, as in first module I give some introduction about that. That is your valence band and conduction band are exactly aligned to each other. Then it is easy to go from electron from valence band to the conduction band, and the photon emission is carried out is there, and that is which is shown in the figure. Indirect bandgap semiconductor, in which if you see that is a valence band and conduction band are not exactly aligned, and so that the indirect bandgap semiconductor, in which that is a phonon assisted transition is there, means both momentum and energy both are not conserved, as in case in direct bandgap semiconductor. There is a radiative recombination in direct bandgap. Here is a non-radiative, that's why in direct bandgap, which is showing a very good optical property, that is a good photoluminescence property, so that it is explored for many applications such as light emitting diodes, then diode laser, and where the photoluminescence property is important, then that time direct bandgap semiconductor is used. Indirect bandgap semiconductor, in which do not have a good photoluminescence property, so it is not used in that places. Then probability of radiative recombination, as told, it is very high in case of direct bandgap, it is very low here. For example, you take example of like CDS, TiO2, ZNO, then CDT, CDC are the direct bandgap cell. Here is the silicon and germanium are indirect bandgap cell. Then thermal recombination process, if you see in PN junction, that is PN junction, one property is very important, they are rectifying, that is means allow current only flowing easily in one direction. If you see, this is very basic IV characteristics of forward and reverse junction you studied in 12th standard or in your graduation. Forward bias, in which that is more current you are getting, that is current which is in milliampere, and reverse bias, in which we are getting a very, very small current, that is which may be in microampere, and that characteristics which is shown here. And then here show the two regions, that is a P and N type semiconductor, are physically separated. In P type semiconductor, you know, that is a majority charge carriers are the holes and minority charge carriers are the electron. In N type semiconductor, your majority charge carriers the electron and minority carriers are the holes are there. Here that is the energy diagram showing that is in P type, that is your Fermi level which is near to the conduction valence band edge, and in N type semiconductor your Fermi level which is near to the conduction band edge. Then here see, that is because in this PN junction module mainly will deal with the depletion region, or that is also called as a space charge region. Then you see here in the upper figure, the electric field in the depletion region are when we join together P and N type semiconductor, the large carrier concentration gradient are there. So the holes from P side can diffuse into N side, and electrons from N side can be diffused into hole side. The continuous process is there, and due to this diffusion, the hole continually live in the P side, that is a negative exciter, and here we are similarly in the N side, that is the your positive donor are there. And then this space charge, or that is called depletion region, space charge or region creates an electric field. Due to this E is electric field directed from positive negative charge toward the negative charge, which is as shown in the figure. Then below figure, in which there is a band bending is arises due to the due to here, that is electric field is which is created here, a drift current and diffusion current, which is oppositely to each other when electron will go from valence band to the conduction band, and which is given here, that is when there is a hole, and the diffusion and your drift current, in which carriers are exactly opposite, and that is no doubt that is a density, current density is become a zero. Then here, as previous slide I already told this, that each type of carrier drift current due to the electric field must be exactly cancelled with the diffusion current. Here we calculate the current density due to the holes, and jp for drift current and jp for diffusion, which is opposite directed to each other. Then this equation we written, q mu of p is the mobility of holes. We gone through this equation in the first module. Dp is a coefficient of diffusion, or is also called as a diffusivity. And then from this, by using Einstein's relation, we show that Jp is equal to 0. And then we know the equation for holes, P is equal to NIE. That equation, if you take its derivative, then we can write, which gives Jp is equal to 0. And similarly, we can write the same equation for the net electron current density, that is Jn is equal to 0. And which shows that here, the condition of zero net electron and low hole current, the Fermi level must be constant, means Fermi level is independent of a distance, that is x, throughout the sample of a semiconductor material, as shown in the diagram. Then here constant Fermi level required thermal equilibrium results in charge distribution, that is a metallurgical junction where Nd is equal to N, your Na is a concentration, that is a that is nothing but in the depletion region or in space charge region. Now we have to calculate the unique space charge distribution in the electrostatic potential. That is psi is electrostatic potential. That is using Poisson equation d2 psi by dx square, which write for the Nd minus Na plus P minus N, that is called as a profile here of that is electron and holes, that is a doping profile is there, and here which is showing q of psi p, which is below figure, q of psi p and q of psi n. Now we have to calculate the electrostatic potential for the hole and electron, where we have to assume that the both donors and acceptors are ionized. Then in regions away from this metallurgical junction, we are Nd metallurgical junction, we are donor concentration and acceptor concentration, which is same, and that's why the charge neutrality is maintained in the total space region, that is the density is 0, as we shown Jp and Jn is equal to 0. For this neutral region, we can add dt psi by dx square is equal to 0. That's why Nd minus Na plus P minus N is equal to 0. So that P type neutral region where Nd is equal to 0, because in P type there is a hole, holes are majority carriers, and so we can write psi of P in this equation by using above equation minus KTQ ln Na by Ni, where Ni is the intrinsic carrier concentration. Similar equation we can write for the N type neutral region, psi n is equal to minus Kt by Q ln Nd by Na. By using that, we have to calculate the built-in potential, or by using psi p plus psi n, we are getting that your built-in potential, which is shown in the next slide. Then total electrostatic potential difference between P and N side, we calculated VBI psi n minus of psi p, that is a Kt minus Q ln Na Nd Ni square. And from this regions here, neutral region of a P and neutral region of R, where transition region which is shown in the both, when electron go from valence band to the conduction band, then charge density due to this uncompensated impurities, that is Nd and Na, then here space charge is denoted, and this transition region where completely depleted region, where in that region, depletion region, your charge carrier densities are 0, that is Jp and Jn is 0. That region is called as a space charge region. Then typically in PN junction, like for example, you take example silicon and germanium, with the width of each transition is small. That's why the width of depletion region is like a rectangular approximation. By using this above equation with completely depleted region in above Poisson equation, if we see, then P and N is equal to 0, so that your Poisson equation is become only the first term is present is there, and neutral and p region which is shown in the figure. Then basic device technology means how fabrication of a PN junction or PN junction is how fabricated. There are four mainly steps are there. First step alloy junction, second step is the diffuse junction, then diffuse planar junction, third step and fourth step is a diffuse planar junction, and epitaxial substrate means substrate on which you are making your PN junction. The first step in which n-type semiconductor in which you have to put the aluminum as pelleted aluminum with there are conditions are there, temperature conditions are there, then Si alloy form, then we again put the p type of semiconductor there, then n type and p type with alloy is forming. Then second is a diffuse junction in which same n type silicon in which we are impurities are diffused into p types, and then that is a pn PN junction is formed, but there is also another problem, that is SiO2 insulating ray is putting. Then this number of process, then finally you are forming your PN. Finally you are fabricate, that is a PN junction is there, and that is which is shown in the figure, that is in fourth stage, that is a diffuse planar junction on a substrate. Then based on the built-in potential formula, we have a numerical calculate the built-in potential for silicon PN junction with with acceptor concentration 10 to 18 per centimeter cube and donor concentration 10 to 15 centimeter cube. Then by using our formula, VBI is equal to KT by Q ln Na Nd divided by Ni square, where Ni is intrinsic carrier concentration and that value is a 9.65 10 to 9. By using that you are getting, but solve in the notebook, and that is you have to thoroughly solve it and get answer it and check the answer. Then your 0.774 volt is coming as shown in figure here. NaNd, that is acceptor and donor concentration shown in y-axis, and psi p and psi n, that is electrostatic potential for electron hole in y-axis. Then here built-in potential whatever we calculate by using VBI, here exactly we are getting the same value, means for because here doping concentration in the electrostatic potential of gallium arsenide which is higher because of its a smaller intrinsic concentration. Here in case of its built-in potential value is 0.774 0.77 volt only, but in case of gallium arsenide it is a higher value because of smaller intrinsic carrier concentration. And then for this today's lecture I use that is specially book, that is Z book. I number of things gone from that, and that is you have to go thoroughly with this lecture and do study is very important, and thank you.